A pleasant day, everyone. Welcome once again to our lecture for today. So last time we talked about motion along a line, or that is referred to as rectilinear motion. So I'd like to give emphasis more on what we had discussed last time. Um, I'm going to show you something, the basic concept of rectilinear motion, why we came up with those formula. So in this presentation, you will be able to understand more on what is this instantaneous velocity and also the average velocity referred to the given figures. Alright, so particle moving along a straight line is said to be in rectilinear motion or motion along a line. Right, we have here the illustration. This is our coordinate axis, x-axis, and we have what we call here O, that is the origin where the particle is moving, positioning at t equal to 0 before it moves. It is at this position. Then at t equal to, or at some time t, the particle moves going to the right with this distance covered. We call it x. Right. So by the way, let this distance be equal to 1 meter. Okay. So this is the concept class. Position coordinate of a particle is defined by positive or negative distance of a particle from a fixed origin on the line. Okay, so if the particle moves to the right, if this is the origin, so this is positive, going to the left, negative. So refer to the fixed point, we call it origin. Okay, so the motion of particle is known if the position coordinate for particle is known for every value of time t. So motion of particle may be expressed in the form of a function. For example, something like this: x equal to 6t squared minus t cubed. In our previous video, so we use here on the left side as s. S is the position, right? But now we use x, so don't be confused. So it can be any variable. We just defined what is that variable represent to. So in this case, we let x be the position of the particle with respect to time. So this is in the form of a function. So the position of the particle is expressed in terms of this function, x equal to 6t squared minus t cubed. Or in the form of graphs, or in the form of a graph. So x versus t graph, something like this. So we have here x as our vertical line, vertical axis. X is for the position, that is in terms of meters, and the horizontal axis we call it t for the time, t in seconds. S here is in seconds. All right. Now consider particle which occupies position p at time t. Okay, so we have here a time t. Okay, consider a particle which occupies position p at time t. Okay, at time t, it means from the origin, the particle or a particle moves from the origin towards this, covering a distance or a position equal to x, and of course it spends time. The time to reach at this position p is equal to t. Now if it moves further, so there's a change in the position, so the change in position we call it delta x. So of course there's also a change in time, we call it delta t. So the t here, class, is the distance from the origin O towards this position. So this is our t, right? Sorry, the time t. Okay, So that is the time spent to reach at this position, point P. So that's why we have here t plus delta t, because the change, when there's a change in position delta x, there is a corresponding change of the time spent. We call it delta t. Okay, so that's why we have at position p prime. Okay, so we have t plus delta t. It means that from here, referring from the origin also, so the total time spent to reach in that position is equal to t plus delta t. All right. Okay, so I hope it's clear with your class. Okay, so the average velocity, when you speak of average velocity, so in our previous example, we just subtract the final distance with the initial distance divided by um, final time. We have tf minus initial time ti. But this time, so this is clearly shown in this illustration that the average velocity is simply the ratio of the delta x, change in the position delta x, divided by delta t. Alright. Now when you speak of instantaneous velocity, so that is where we use our calculus. So the instantaneous velocity, we have v, or in our previous discussion we use v sub t, right? So this is equal to the limit of this ratio, or the limit of this, as delta t approaches to zero. So that is what we call instantaneous velocity. So in our previous discussion, we use instantaneous velocity. We represent it by this expression or notation v sub t. Okay, so here we have instantaneous velocity equal to v equal to the limit of the average velocity, which is delta x divided by delta t. Taking the limit on this ratio as delta t approaches to zero, so that is our instantaneous velocity. Alright? Now, instantaneous velocity may be positive or negative. It can be positive or negative. It depends on the direction. It depends on the value of our v. Now, for our v, when this v is less than 0, when v is less than 0, so what does it mean, v less than 0? It means that the value of our v is negative. So, referring to this illustration, okay, so this is our p moving, or the v is on the left side, because this is negative, assuming this is the neutral point, the initial position of the particle. So if it is on the left of this p, so it means that our v is negative. So the instantaneous velocity may be positive or negative, so depending on the value of our v. So if our v is greater than 0, okay, so what does it mean? When v is greater than 0, so it's positive, or v is positive, so it means that the particle is moving from left to right. Here, the particle is moving from right to left. Okay, so right to left or left to right, so it depends. Huh? And magnitude of velocity is referred to as particle speed. Okay, that's referred to as particle speed. So that is the magnitude. So magnitude of velocity, because when you speak of speed, that is just a scalar. When we speak of velocity, especially if that is expressed in terms of vector, so that is composed of magnitude and direction. So the magnitude there is what we call the speed. Alright? Now from the definition of a derivative, so we have v equal to the limit of delta x divided by delta t. as delta t approaches to 0. So referring to our previous discussion about derivative, so it means that this is the dx over dt. So dx over dt is the derivative of whatever is the value of our position of the function. So if the function x is expressed in terms of time, so when you take the derivative of that function, for example, our function is x as a function of time. So when you take the derivative of this x with respect to time, then we have the velocity. Okay? So v is equal to the limit of delta x over delta t as delta t approaches to 0, and this is our derivative, the derivative of our function. Our function, for example, is x of t. For example, if you are given, say, x, the position x is equal to 6t squared minus t cubed. Now, if you're going to find the velocity, so you just take the derivative of x with respect to time. So, derivative of x with respect to time, we have v, that is equivalent to v. Okay, that is the velocity. So, taking the derivative of this, applying the constant multiple rule and the power rule. So, we have this power will go down and multiplied by 6 and t. So, you have 12t minus. So, power rule applies. So, you have 3t squared. So, that is our velocity. So, the velocity is, that is 12t minus 3t squared. So, this is our v, which is equivalent to the, or equal to the derivative of the position with respect to time. Now, if you are going to graph that, so we have here the graph v, the vertical, okay, in terms of meter per second. Okay, and then we have here the horizontal, that is our t, that is the time in terms of seconds. So for example, if when t is equal to 0, so when t equal to 0, using this is the velocity, so you look at the expression of the velocity. Velocity is equal to 12t minus 3t squared. So when t is equal to 0, so what is our v? V is also 0, so at this point. But when t is equal to 2, so when t is equal to 2, so 12 times 2, 24, minus 3 times 2 squared, so 2 squared is 4, times 3, 12. So 24 minus 12, that is 12. So that's why we have at this point here. Okay, so initially at this point, t equal to 2, so at this point. When t is equal to 4, so 4, 12 times 4 is 48. So minus 3 times 4 squared, 16. 16 times 3 is 48. So 48 minus 48 is equal to 0. Okay, so you have at this point. So when t is equal to 6, so when t is equal to 6, so 12 times 6, what is 12 times 6? So 12 times 6 is 72. Okay, and then we have 3 times 6 squared. So 3 times 6 squared. So 3 times 6 squared, 6 squared, 36. 36 times 3. So 108, right? So 72 minus 108. So what's the difference? So that is equal to negative 36. So that's why we have here negative 36. Okay? So when t equal to 6, our velocity is negative 36. So connecting these points, so we have the graph of the velocity function. Okay? So this is the graph of the velocity function. Alright? So when you graph the velocity function, it looks like this. Considering this given position function. Okay, this is our position function. Okay. Next, consider particle when velocity v at t and v prime at t plus delta t. Okay, so we have this illustration here. So now at we have the position of the, or the velocity of the particle at p equal to t. Then as it moves, when it change the, so when you speak of velocity, that is the change of a distance with respect to time. So when it changes the distance with respect to time, so it travels, so this is the delta t. So it means that traveling from this position to this position, from p to p prime, so it spent a time that is equal to t, or delta t. So therefore the distance, or the total time uh, traveled up to this position, the new position, is simply t. Okay, this t here is the distance. So for example, the particle started at this point here, so it travels distance, or the time, sorry, the time, which is t. Okay, so this t here, and then we have a t here. Then if this particle moves further to p prime, so this will be the, okay, let me erase this one first. So this will be the delta t. So therefore the total time traveled by the particle from this position here up to this position, so the total time is simply the sum of the two times. We have t plus delta t, t plus delta t. So that's why in our uh, here we're having t plus delta t. It means that it's a total time spent by the particle changing its position with respect to time. Okay, so from here, the particle is now moving at the velocity v plus delta v. All right, so uh, it changed. So it changed. There's a change of the velocity. So we have what we call the change of velocity with respect to time. Okay, so there's a change of velocity with respect to time. That is what we call instantaneous acceleration. So that's why we have here the definition of instantaneous acceleration equal to a, which is the limit of the change of the velocity with respect to time. Okay, so for this illustration class, we have what we call the acceleration, instantaneous acceleration, which is defined as the limit of the delta v with respect to time, or delta v divided by delta t, as delta t approaches to zero. Okay, so this expression class of our acceleration is referred from this illustration. Now, all right, so I will erase this one so that we have a space for the next information. All right, so we have here instantaneous acceleration may be positive. So positive if increasing positive velocity. So it means if our velocity is increasing, because there are scenario class that the velocity is decreasing. So when we speak of increasing, it means that the velocity is changing, no, from slower to faster. So that is positive. No? If it's from slower speed to faster speed, so it means that the acceleration, or the velocity, is changing uh, from slower to faster. So the acceleration is positive. Okay, so increasing positive velocity. So that is what we call by instantaneous acceleration that is positive. All right. We also have decreasing. So in this scenario, this is decreasing. You see. So we have our acceleration is positive. We have a is greater than 0, but look at the uh, velocity here. The arrow here, the length of the arrow indicates or tells us that it's velocity is faster, and you see here that it moves farther to the left. The arrow here becomes shorter. It means the particle is moving slowly or slowing down. Okay, so this is decreasing. So decreasing negative velocity, right? So we have here positive. There are two scenarios. Increasing positive velocity, like this one. Increasing, you see the arrow here is smaller, all right? And then the arrow here is uh, longer. So it means that increasing positive velocity. So this indicates increasing positive velocity. So our A here is also is greater than 0. So they are on both, or they are on the same directions, the velocity and acceleration, both in the same directions. All right. So this is a scenario where the instantaneous acceleration is positive, and this indicates increasing positive velocity. So another scenario, I'll go back to the other one. So another scenario is we have here acceleration is positive, right? Positive, but this is decreasing. You see, from longer, this longer arrow, so indicates faster velocity than the shorter arrow of v or v prime. So it means that it's slowing down. So it means it's positive but decreasing negative velocity. So our acceleration is still on going on that direction to the right, no, similar to the first scenario. Uh, Going to the right meaning positive. The value of our A is positive. All right. So positive but decreasing negative velocity for the second scenario. And another scenario is something like this. Instantaneous acceleration may be negative. So when this will be negative? So if the acceleration is negative, meaning less than A is less than 0, so our acceleration is negative. And if you look at the arrow, from longer V, longer arrow of V, then to shorter arrow of V. So it means that the velocity is decreasing, but the direction is positive because going to the right. The velocity, the direction of the velocity is going to the right, but decreasing. Okay, so from longer arrow to shorter arrow, that indicates decreasing positive velocity. All right, but our acceleration is negative. Okay, but decreasing positive velocity. Another scenario is something like this. Still, our acceleration is negative, and now the direction of our velocity is going to the left. Okay, going to the left. So again, this falls to this scenario, negative instantaneous acceleration, but this time increasing negative velocity. So you see, small arrow indicates slower, but the second arrow, this is longer, so indicates faster, but going to the left. So negative decreasing positive velocity, or increasing negative velocity. So I repeat to make it clearer. So the first scenario is something like this. Our instantaneous acceleration may be positive. Okay, so may be positive. So there are scenarios here. So one scenario is that increasing positive velocity. Okay, increasing positive velocity. So this is the illustration. So positive or acceleration, because this is A is greater than 0. So positive going to the right, and our velocity, you look at here, a small or shorter arrow, so that indicates slower. Then we have here second position of a particle. It changes, the arrow becomes longer, so it means it increases. So we have positive instantaneous acceleration, increasing positive velocity. Okay, so another scenario is something like this. So still our acceleration is positive, but look at the direction of the velocity. It's going to the left. So initially, it's a longer arrow, so that indicates faster velocity. Okay, and then as it moves in the next position, p prime, so the velocity becomes shorter in terms of arrow, shorter, so it means it's slowing down. Okay, so this is still positive instantaneous acceleration but decreasing negative velocity. Decreasing negative velocity. Another scenario is it can be negative. Instantaneous acceleration may be negative. Okay, so it can be negative. And again, we have two scenarios here. One is decreasing positive velocity. Decreasing positive velocity. It means if you look at this picture, we have a longer arrow, so it means faster. Then in the next position of the particle in the pre-prime, it becomes shorter. So it means that the velocity is decreasing from faster to slower, so decreasing. So negative instantaneous acceleration, decreasing velocity. And the last scenario is something like this. Still our acceleration is negative, so going to the left, and our velocity is also going to the left. So initially our velocity is shorter, the arrow is shorter means slower, and here we have the uh, longer v, v prime, we call it v prime. So we can say that negative instantaneous acceleration or increasing negative velocity. Alright, so these are the scenarios, class. I hope you understand this one because we have an example. After this video, we have another video that will show you an example that will illustrate this principle. Now, from the definition of a derivative, so if we're going to graph the acceleration, so this is the graph. So remember that the acceleration is just the derivative of the velocity. Okay, or that is the change in the velocity with respect to time. So the limit of it. No? So instantaneous acceleration is defined as the limit of the change of the velocity with respect to time as delta t approaches to 0. Or this is the derivative of v with respect to t. Or if you look at x, the position, we know that if you have x as a function of time, when you take the derivative of that, we have the derivative of that function is also a function. It means that the derivative is also a function, so you can take the derivative again with that function. So we call it the second derivative of that function, which is the position x. So in other words, the acceleration, instantaneous acceleration, is the limit of the change of the velocity with respect to time as delta t approaches to 0 equal to the derivative of v with respect to t or the second derivative of x with respect to t. Second derivative, the 2 here indicates that you differentiate twice the function x as a function of time. So take note, you have to be consistent. D, then you have 2 here, then x. Here we have d t squared. Here we have d squared x. We have here d t squared. So that is a different meaning if you have dx squared and dt squared. So this indicates the second derivative. It means you take the derivative of the function x twice with respect to time. Okay, so when you graph this, so you can see the graph of the acceleration looks like this. So taking the same example as in the previous slide, we have v equal to 12t. So this is taken from the x. Remember, our x is, this is taken from our x as a function of time, which is equal to, I think that was 60 squared. I think that was 60 squared. This origin is 60 squared. Then minus, I think this is minus t cubed. Okay, so when you take the derivative of this, so that will become 12t, right? Then this one becomes 3t squared. So that is our x prime, right? Our x prime, as a function of t. So our x as a function of t is this one. Then when you take the derivative of this x as a function of time, so we have equal to 12t. Okay, this is 12t minus 3t squared. So you just take the derivative of the function, this function here. So 3t squared. And we know that the derivative of the position function is just the velocity. So that's why we have here the velocity. Now, if you are going to take the derivative of the velocity, it means, because this is also a function, right? You can differentiate this as differentiate this with respect to time t. So again, when you take the derivative of this x prime, so this will become x double prime, right? This is x double prime. This x double prime, so it means something like this as a function of t. So it means that you have taken the derivative twice of our function x. So when you take the derivative of this, derivative of, what is the derivative of this? So 12t, derivative of 12t is, let's see, that is 12. Okay, so derivative of 12t is 12, then minus, so this is 6t. Okay, 6t. All right, so that's I'm just illustrating, just to relate, no, what this acceleration uh, is telling us in this discussion. I was just showing you that in our previous example we have given something like this. Okay, and then when you take the derivative, you have the velocity, so 12t minus 3t squared. Now when you take the derivative again for the second time, so we have 12 minus 6t. Okay, so therefore, so we have 12t minus 3t squared. So when you take the derivative of this, so that is now the acceleration. So in other words, this one here, so this is actually equivalent to acceleration. So a as a function of t. Or, so from here we have derivative of this. So this is dv over dt, so equal to 12. So minus, so this would be minus 6t. Okay, so if we follow this, if assuming that this is the v. Okay, now if you are going to graph this, so when t equal to 0, okay, just hold on. Okay, so that's correct. Now this is we have a missing 60 here, so I'll just change this color to make it consistent. I use this black, and I will erase this. Okay, so this is minus 60. Okay, so this is the acceleration. Okay, so if we're going to graph it, so assuming we have this, now considering the same example, we are given initially x equal to 60 squared minus t cubed. So consider particle with motion given by this. Okay, so if you are going to graph this one, this is the graph of this given function. So the motion of the particle follow this kind of graph. Alright, so when you substitute values for x equal to 2, for example, or x equal to 0, at x equal to 0, so what will happen? When x equal to 0, Okay, so when x equal to 0, sorry, when t is equal to 0, sorry for that class, when t is equal to 0, so 0 squared, 0, times 6, 0, 0 cubed, 0, so 0 minus 0, 0, so that's why at t equal to 0, so the point is here. When t is equal to 2, so when this is 2, so 2 squared is 4, 6 times 4, 24, then minus 2 cube, 8, so 24 minus 8 is 16, so we have here, okay, so this is 16. Then when x equal to 4, so 4 squared 16, 16 times 6, okay, and then minus 4 cube, which is 64, so the difference is 32, so that's why we have it here. Then when x equal to 6, so 6 squared 36, 36 times 6, so we have that value, then minus 6 cube, then you subtract, so you get this 0. Okay, so that becomes 0. So when you connect the points, so you have this graph. Okay, so this is the graph of the function of the particle motion. Okay, now from here, if you are going to determine the velocity, you just take the derivative of this. So the derivative of um, x with respect to t, so you have now dx over dt. Okay, so we have dx, so the derivative of x with respect to time, so that is called dx over dt. So what is our dx over dt? So applying the sum rule, so we have dx over dt is 12, no? This 2 will go down, multiplied by 6 is 12 times t. So 12t, this will go down, so 3t squared. So derivative of x with respect to t, meaning the derivative of this one is equivalent to the velocity. Okay, so when you graph this, this is the graph of the velocity, which was shown in our previous slide. Now, if you take the derivative of this, from this velocity, this is the velocity. So the derivative of velocity with respect to time is just the same as the second derivative. This is the first derivative. The first derivative of x. Now, taking the second derivative of x, second derivative, this is the first derivative. This is also a function. When you take the derivative of this, so derivative of 12t is 12. Derivative of 3t squared is 60. So we have now what we call the instantaneous acceleration. Okay, this is the instantaneous velocity. This is the position. Okay, so when you graph this, it will look like this, class. Okay, so we have done this in the previous slide, so I will not repeat that anymore. Okay, so these are the values that we have tried. When you substitute this, you will see this graph. Okay, so I think that's all for this video now. I'm just emphasizing the topic or the some example that we have discussed in the previous video about motion along a line. Okay, so thank you very much. See you again in the next video. I will give you some example. Let's see if you really was able to uh, catch up and understood the discussion, class. Okay, so once again, class, stay safe and healthy always. God bless. Bye.